Hello, this is checkpoint 4.22. They want us to find a differential dz of the function, and the function is going to be f of xy is equal to 4y squared plus x squared y minus 2xy. And they want us to use it to approximate the delta z at the point 1 comma negative 1. All right, what is dz? dz is the differential. This is going to be defined by f sub x evaluated at some x naught y naught times delta z, or dz, or dx, sorry, plus the derivative with respect to y evaluated at x naught y naught times dy. Now, it turns out that the delta z and the delta y are equal to dz and dy when we come down to it. Maybe we can make that as a little note on the side to say that dx is equal to delta x, dy is equal to delta y, and that happens for the independent variables, whereas the dz is only approximately equal to delta z. That's the dependent variable. So we'll keep that in mind. Meanwhile, we need to take some derivatives. So the derivative with respect to x, f sub x, will be equal to, the first term is gone. We have x squared times y. So that's going to be, the derivative of that is 2xy, and then 2y minus 2y. So this is our differential, and well, this is our derivative with respect to x. We'll take the derivative with respect to y. F sub y will be equal to, the first term is going to be 8y, and then the second term will be x squared positive, and then the last term would be minus 2x. So before we put in the values, we can actually express the differential dz is equal to 2xy minus 2y dx plus 8y plus x squared minus 2x dy. So this is actually a differential, and it can come up in other classes like differential equations, where we would try to recover the original function from this differential. Okay, but we're not doing that. We are interested in evaluating these things at the point negative 1 comma negative 1. So let's evaluate that. F sub x at 1 comma negative 1. You put a positive 1 in for x and a negative 1 in for y. And we have 2 times 1 times negative 1 minus 2 times negative 1. So we get a negative 2, and this is going to be a positive 2. So negative 2, positive 2 is 0. That is our dx, and or that's going to be our f of x. Our f of y is going to be 2, it's going to be 8 times y plus 1 squared minus 2 times 1. We're going to get negative 8. Negative 8 plus 1 minus 2, so negative 8 minus 1, that's negative 9. Okay. Therefore, our differential dz, specifically at this point, is going to be equal to, and we want to approximate this at this point, and when delta x is equal to 0.03 and delta y is equal to negative 0.02. Okay, so we have 0 times delta x. Well, it's not going to matter because it's going to be 0. And then we have negative 9 times delta y, negative 0.02. And this will end up being positive 0.18. Okay, so this is our dz. Now we want to use it to approximate delta z. It turns out that another formula that will be useful for us is to say that the delta z is actually equal to the actual function evaluated at x naught, and then you move by a delta x direction, and then y naught, and then you move by a delta y direction. So this gives us the actual function evaluated, and then we want to subtract off our dz, or we want to subtract off our f of x naught, or f of x naught y naught. Okay, and we need to put these things into the function. Our x naught was positive 1, so we have a 1 plus 0.03, so that's 1.03 comma, and then we have a negative 1 minus 0.02, so it's negative 1.02 minus f of 1 comma negative 1. All right, so it's just a matter of putting it into the function, and I ended up doing that, and I used my calculator to eventually get this to, let's put a dot 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 here and say this is equal to 0.18068. Okay, and the idea is to compare this and to see that we got a pretty good approximation using our differential and compare it to the actual value. Okay, I hope that helps.